because we have a speaker who, though he's an external speaker, we consider him all the time as our in-house, because he has been our product as regards to he has done his master's from this place. He has done his PhD from this place. Right now he is with PES University. He is an associate professor, and he was a faculty, consulting faculty over here in the VLSI design and he has been responsible for establishing our VLSI labs. I mean, along with Professor Askant, me and all others. So what is important is that Dr. Sudeendra would be talking on hardware security, but side by side he'd also be focusing on to that how this be relevant for Internet of Things. And that is what is the theme about this particular topic. I mean, the whole FDP is on about. Yesterday we had listened to Professor Anirban Sengupta, who talked about hardware security out and out. And now Dr. Sudeendra Kumar will be talking on the hardware security aspect, because hardware security, as you have seen, is a vast subject. But then wherever is the applicability is there, you will be taking and touching upon. So now over to Professor Askant. He will be reading out a brief biodata and introducing Dr. Sudeendra Kumar formally. Then our lecture would start.
Yeah, thank you, sir. May I request Professor Sudeendra to...
Thank you very much, sir. It's all your blessing, sir.
No, that's fine. Go ahead. Okay,
Yeah,
please go ahead.
Thank you, sir. Professor Sudeendra, may I request you to switch on camera for at least for introduction period, then you can switch it on, if possible.
Sure, sir.
Yeah, thank you. So today I feel honored to invite Professor Sudeendra Kumar K for our lecture on ATAL FDP hardware security for Internet of Things. Sudeendra Kumar K received BE from VTU and holds master's and doctoral degrees from NIT Rourkela. He started his career with Wipro Biomed, Bangalore, worked with Beckman Limited Equipment. His professional career includes a stint as application engineer for Freescale Semiconductors and product test engineer for Qualcomm. He has got significant experience in special manpower development project 2, that is SMDP2, and SMDP chip 2 system development project under the aegis of Ministry of Communication and Information Technology, GOI. He was responsible in establishing VLSI labs, training on EDA tools, chip design, and tape out. He has got more than 30 publications in reputed journals and conferences, and also a reviewer for the Elsevier VLSI Integration Journal, IEEE Consumer Electronics Magazine, and IEEE Transactions for Emerging Computing Systems. Currently, he is Joint Domain Head of VLSI and Embedded Systems in the Department of Electronics and Communication Engineering, PES University, Bangalore. So I request Professor Sudeendra, please share your slide and start your talk.
Sir, thank you very much for the generous introduction, sir. Thank you very much. Sir, I'm sharing my screen.
Yes, sir.
I hope I am audible and my screen is visible.
Yes. Okay, fine.
Can we start, sir?
Yes,
Sudeendra, please go ahead.
Yes, yeah. So, okay. One second, I will just turn off my camera. Good evening, everyone. Good evening, sir, and good evening, Aiskan sir also. So now the topic is the securing IoT edge node. And before getting into the IoT, securing the IoT edge node, first we can look into the outline. That is what we are going to cover. That is IoT and security in IoT. And actually, before getting into the actual IoT and all, three things we have to discuss. And the outline itself, I just made 3 points, which is unconventional. That is, we know cyber physical systems in the as early as in the research literature we can find about cyber physical systems during the World War itself, during the Second World War itself, between that is 1940 and 50s. The case is whenever the analog computer was designed and analog computer was available, the connecting sensors and getting data was already started. And again, that is actually the starting point of cyber physical systems. It means the using this analog computers or large digital computers, we can say, or analog computers. The first thing which got automated in the factory was a bottling plant. It may be a Coca-Cola bottling plant or the '60s. Means it started somewhere in late 50s, but again it was very predominant in Western countries like United States of America and all, where exactly the bottling plant started getting automated in 1950s and 60s. That is where exactly we can find the actual application of cyber physical systems in a very large scale with using the computers of those days of early 60s. So we know this connecting to the sensor and again taking a action, means processing the sensor data and acting on the sensor data and communicating it to the actuator and taking a control action and also storing the data was all started in the early 60s itself in cyber physical systems. Example, as I mentioned it, in the bottling plants in the United States of America. But gradually it got improved, and again as the computer technology improved, we just get into the Intel microprocessors was came into existence. Gradually the cyber physical systems also got advanced. Not only the bottling plants and more and all other manufacturing systems, from car manufacturing to all other manufacturing systems get lot of automation component in them. And again, especially when it comes to the Toyota, they call it as a light what is that, what we call it as a light conveyor. Means just they will have a light supply chain and all this part of an automation which created, which was made possible through sensors and computers. Large factories are automated to larger extents in Japan, America, and all by the 1980s. But the case is, once we the 1980s. But the problem with this cyber physical systems is there from last 70 years. But at the same time, we came across something called as a new buzzword in early 90s and till it continued up to 2010. That what we call as an embedded system. Means if you have a large, let's take one example which I have practically seen in one of my in my early career was, I saw the one 8085 board in one of the e-treatment plant in Bangalore. That it had it has a data acquisition system. If more, that PCB was more than my laptop size, whatever the dimensions of laptop, whatever the laptops we use today, that was much bigger than that PCB size was much bigger than the laptop size today. Means it was just a data acquisition system. It had a 8085 microprocessor on it, a sufficient amount of RAM, ROM, peripheral, PPIs, ADC, RS-232 interface, power supply, and other protection circuits, etc. And all. It made a large PCB, which is almost half of a table size, half of a normal working table size or something like that. So that got replaced. We replaced that large board with a small palm size PCB, where all components, that is ADC, this memory, PPIs, drivers, memory, everything got integrated into the single chip. Then the people started in the common way, that is an embedded system. So this continued up to this early 90s, means till 2000. From early 90s to till 2000, the cyber physical systems was the terminology faded away a little bit, but still it was used in the research literatures, especially from the control system and system engineering researchers. But embedded systems was a buzzword in for 20 years till 1990s to the early 2011, 2012. But this Internet of Things word was coined in 2012, and it became very popular and a buzzword after 2014. So actually we have a same logic, that is cyber physical systems connecting to server, processing data, take action and give a signal to the actuator, store the data, analyze up to some extent is done in CPS. And in embedded systems also we do relatively same at a cyber physical systems looks large. Embedded systems will do that one in a small scale systems or smalls in a looks small physically, but it does large scale data also. But then again, the embedded systems got promoted to something called as the Internet of Things. Why this Internet of Things was not there before 2012? Why it was coined in 2012? And 20 years we have embedded systems. Before that, we named it as a cyber physical systems. So this is actually a gross history of we started from cyber physical systems and we reached Internet of Things in 2014 or 2013 and all. So why we reached this place? Why it was? What are the factors which or emergence which led to the emergence of Internet of Things, or why it is, how it is different from embedded systems, and how it is different from cyber physical systems? That's what exactly we can discuss in the initial part of this lecture. So the IoT and Internet of Things and cyber physical systems. Basically the IoT, the concept of IoT is very similar to the CPS, because CPS is an integration of sensors, actuators, communication networks, and control systems in which status of a physical system is monitored with the help of sensors and suitable control action is taken. But the problem is, the IoT is also similar. We connect sensors, we do everything. Means whatever the definition we have CPS, it is also very similar to the IoT, what we are doing today. But CPS is well established domain and has got a numerous applications like factory automation, etc. But where exactly the IoT comes into the picture? How it is different from the CPS, a conventional CPS of which we know from last 70 years. So the IoT is very different from CPS in terms of number of systems connected to the communication link. Read it as an internet, the amount of data generated, and scope for scalability at the normal term. But at a larger scale, at a gross way, we can define CPS as a system infrastructure and IoT is a networking infrastructure, and connected to the large number of devices when compared to the CPS. Then generally the CPS connects to mainly the CNC lathe or some eating furnace, or else in a bottling plant it will just check whether the bottle sensor is there or not. If bottle is there, just pump the Coca-Cola juice into the bottle, then move the conveyor. After moving the conveyor, when we'll move the conveyor and the weight of the bottle increases, then you move the conveyor, so the next bottle will come to the filling the juice. Then again the juice will be filled, then again it go to the next bottle. So in this way, actually we have a weight sensor, we have a bottle sensor, maybe the photo detector will work for that when bottle is ready or not at the particular place. So like this, a very minimum number of systems are connected to the CPS. May not be through the internet, it may be through the Modbus or a Profibus, which is a standard interface in in the factories even today. So, but in the case of IoT, it's an internet. It's a IPv6 or IPv4, this normal Ethernet connection. So here the case is the CPS is a very number of systems connected is very less, but in IoT we have connected with a lot of nodes through internet, and the scalability, internet is scalable, but CPS is fixed for a particular application. That's the reason why we call CPS is a system infrastructure, but IoT is a networking infrastructure connected to the large number of devices when compared to the CPS. And for CPS, the real-time control is a primary goal most of the time, but IoT, real-time control is not a primary goal, while in IoT, resource sharing, data sharing, effective data crunching with minimum latency are important. Especially here, the amount of data getting generated is enormous in in the case of IoT, but it is very less in the CPS. And again, there the control action is very important in CPS. But here it is crunching, analyzing data, and taking a action based on the data analysis is more important in Internet of Things. This is a gross review between the IoT and cyber physical systems. In the same way, we can take up IoT and embedded systems. How the embedded systems and IoT are differ? More or less, the major difference at a common sense level is embedded systems. If you make it connected to the Ethernet and connected to the cloud, if you have a very good Ethernet connection to an embedded system, then connected to the cloud computing, the cloud storage, then again it becomes it becomes an IoT. How do you convert at a very gross level, very basic level? How do you convert a small embedded system into an IoT? Connect an internet to it, connect it to this cloud storage. Yes, that makes embedded system as an IoT at the very basic level. So, but very advanced level, how it is different. In IoT, the connectivity is important, collection of data is important. In embedded systems, in most of the applications, real-time control is important, and the power is important, low power is important. Even in IoT, the low power is important. But still, the connectivity, the connection and storage capacity makes the IoT much different from the embedded system. Embedded system is a constrained system where we have a limited memory, a limited processing power, and when compared to the IoT, the limited processing power, limited memory, and stringent latencies in most of the applications, where these things are not applicable to the IoT for various reasons. We will see it in the upcoming slides. So this is the difference between how do you differentiate between IoT and cyber physical system and IoT and embedded systems. So the next, why it, as already I asked the question that after 2012, why the IoT came into the existence? Why the IoT came into the existence? Why not before 2012? Why not before 2010? The factors responsible for emergence of IoT are three. That is availability of high performance processors at low prices. This we can see this. We can observe from last 20 years. We can observe during when I was an engineering student, I used to buy a 8051 microcontroller at 60 rupees. 8051 microcontroller at 60 rupees or 70 rupees. But if you go it in a bulk, 8051 was sold at 6 rupees, 7 rupees. Even in those 20 years back, if you are buying a 10,000 microcontroller, somebody easily can get a 10 rupees per microcontroller was possible in 2005 itself. But that was only applicable to the 8-bit and 16-bit microcontrollers. But when you go to the ARM 32-bit microprocessor or PowerPC, a 32-bit microprocessor, or any advanced microprocessor with high performance feature like ARM microprocessor, ARM7 or ARM9 or ARM11 series, I am talking about 2005, 2006. During those times, the cost of, even though if you buy one ARM processor, cost is around 600, 700 rupees. Even if you buy bulk 10,000 microprocessors of ARM microprocessors, price was not coming down below 300. The price was somewhere around 300 to 400 rupees per processor, even if you purchase in bulk. So that was actually the costly. That high performance processors, ARM was a costly, and also there was a lot of hiccups. Lot of hiccups means like JTAG license we need. Means if you want to debug an ARM processor in the very early days, and I'm talking about take a 2001, 2002, or 2003, 4, early 2000s, we need a JTAG license. We have to pay for a separate JTAG license for our JTAG device itself was costly. We were supposed to pay for a JTAG license to debug in high performance processors like ARM. So the cost of hardware and the cost of debugging software, the cost of the associated development, cost associated with the development of designs using very high performance processors was very costly. But now take ESP32, a RISC-V based 32-bit high performance processor, we can buy it at somewhere around 600 rupees. So the cost of availability of high performance processors at lower prices, that's the first thing which is a first factor which is responsible for the emergence of IoT. The next, For the first time, I learned about the cloud computing in 2009. And again, I saw some EDA companies putting their tools on the cloud in 2010. And again, gradually, commercial clouds came into existence, like Amazon, Microsoft, Google, and all came into existence somewhere in 2010-11. Then gradually, the cloud computing or a cloud storage become a ubiquitous thing. But still, everybody from mobile, when we can connect to the cloud, we can get the data from the cloud, and we can put the data into the cloud. So the cloud is a enormous storage capacity, means unlimited storage capacity. The next is another biggest thing which promoted the emergence of IoT is the communication system. That is advances in the internet speeds in terms of 4G or 5G, these things. And device, an embedded system is available. You have an high-speed internet. You have an high-speed internet. It's a real-time internet, and you have an enormous storage. And again, you have an enormous computing power, also in the cloud. You have an enormous computing power and enormous unlimited computing power in the cloud, and again, unlimited memory in the cloud. So this embedded system, which was constrained by memory and computing power with 8-bit and 16-bit microprocessors, now you can afford a 32-bit processor, so that the 32-bit processor can manage high-speed internet, because its processing power is reasonably high to manage the high-speed internet. Through high-speed internet, you are connecting to the cloud, so it has got a enormous computing power and enormous storage. So this, then okay, fine, we have a very good processor. Most of the things are done in the edge level, that is at the ARM processor on my board, on my small PCB board. Wherever required for large scale data crunching or the big data analytics, we are depending upon the cloud. So this takes the control action where, as and when required, it will also talk to the cloud through an high-speed internet in real time. So this changed. Actually, this changed the thinking of this changed a lot of things which made redefining the products and services in most of the application verticals of semiconductor, like automotives, communication systems, and networking systems, medical electronics, then consumer electronics, military and defense. Everybody, it actually, these are the three factors where exactly it was pushed that to coin the term Internet of Things. All these factors made the concept of IoT into the reality, which is redefining the products and services in most of the application verticals of semiconductors. Three, if I summarize, high performance processors, cloud, enormous memory, then again, communication system, Ethernet to connect to the cloud. These are the three reasons why we have IoTs today, which is the redefining all the products and service across application verticals of semiconductor. So these are the networking perspective. Basically, then there are a lot of networks which got merged into the IoT today. See, these are the networks which we have. We used to learn, or we used to discuss about these networks in our 15 years back or something like that. Sensor wireless networking, home wireless networks, disaster rescue networks, defense battlefield networks, mobile phone to peer. All these kind of networks got merged into the Internet of Things, because just a reliable high-speed internet is available. Reliable high-speed internet is available. So this is all these things got merged actually into the IoT in one or the other way. The next is how exactly the IoTs came. Okay, IoTs came, we have high-speed internet, cloud is there, processing power is there. What are the initial thinking of IoT designers? What we can do with these three things? If this, okay, what we can do this with three things, the three major things which came into existence, the first applications of IoT. I'm talking about, for example, in 2015 or 2014, the Barcelona in Spain became the first smart city with 75,000 sensors connected across the city. So that was the first smart city with the concept of IoT getting deployed, the Barcelona. So this case, first they had a cloud, they have a pollution monitoring system, lake monitoring system, vehicle transport system. Exactly all these things are managed. And again, the first IoT concept, the usage of high-speed internet, usage of cloud, usage of embedded systems, all together came in the smart city, smart grid, and smart transport. Smart grid was first implemented in Germany very successfully, where each individual residence is a not only the buyer of electricity, he is also a seller of electricity. He sell electricity to the grid through his solar or any other solar, especially the renewable energy sources, and also he will draw the electricity from the grid for his applications. So at the end of the day, it is calculated whether the grid has to pay money or the consumer will pay money, something like that. It is balanced. So that's a smart grid. Then again, smart transport, like smart traffic management systems, adaptive traffic controller, and all these things are the first initially IoT applications. For example, classical example is the Barcelona smart city project in the early 2015 or in the late 2014. So this concept, this we can call it as a community IoT. Here, one of the biggest fighting or the contention, bone of contention was ownership of data. For example, if I have I have a smart city project. I generate a data. I generate a water pollution in lakes. I will collect the data of a city at different places. What is the air pollution? And again, I will collect the garbage data. I will collect the traffic data. All these things are there. For example, I will deploy as a company, as a firm. I will sit with municipality. I will work with municipality and I will deploy the systems. So data is getting generated. The question is, who is the owner of the data? The ownership of data generated out of community IoTs like smart city, smart grid, smart transport was a debated topic for a long time. And now it is clearly concluded that it belongs to the community, where most of the companies got disappointed. Most of the companies got disappointed because they cannot sell data for others. They cannot sell data by selling data in the initial years of these applications like smart city, smart grid, and smart transport. By selling data, the companies made a huge money. For example, in Rourkela, if somebody implements, or in Bhubaneswar, if somebody implements a smart city project, who is the owner of the data? Bhubaneswar Municipal Corporation or Rourkela Municipal Corporation is the owner of the data. So the local administration, for example, if Bhubaneswar implements a smart traffic management system, like identifying no helmet, triple riding, overspeed, no seat belt, like this, they are automatically detecting and creating a proof in the form of video and images and finding the people. They are collecting data. Means using that data, somebody can easily study the motorization pattern of Bhubaneswar city. The motorization pattern of Bhubaneswar city is available, then it is a marketing component for two-wheeler sellers and four-wheeler sellers, four-wheeler manufacturers and two-wheeler manufacturers. What is the motorization pattern of a Bhubaneswar city, and how it can be used to sell more vehicles in Bhubaneswar city? What is the psychology of Bhubaneswar city citizens in buying the vehicles? A lot of things they will get it from the traffic data. Actually, the traffic violation data, if it is available to the uh, companies like Maruti Suzuki, as just an example, nothing, or Hyundai or Mercedes Benz, they understand what is the motorization pattern of a Bhubaneswar city, and again they can make the marketing strategies for that. But whether the company which implemented the smart traffic in Bhubaneswar city can sell the data? No, because the traffic violation data, the ownership lies with Bhubaneswar Traffic Police. Bhubaneswar Traffic Police. Without consent of the Bhubaneswar Traffic Police, a company cannot sell the data to anybody. So this is where the bone of contention between the companies and community IoT projects came into existence. And most of the companies got disheartened that when it was decided that local administration will have a complete right on data generated, and not the organization or the firms which deployed the IoT services. So with this community IoTs, a lot of IoTs came into existence. A lot of different types of IoTs came into existence. This is a taxonomy of IoTs. One, already we discussed community IoTs, that is smart cities, smart transport, smart grid, etc. The next thing is consumer IoT, then commercial IoTs and industrial IoTs. So this is the broad categorization or a broad taxonomy of IoTs. Hope my screen is visible and I am audible. Anyone can respond. Hello.
Here. Yes.
Yeah. Okay, sir. Thank you. So this is a community IoT, which we already discussed. Broad categorization is four. That is community, consumer, commercial, and industry. So the first we'll take a consumer IoT and understand what this consumer IoT is. The consumer IoT currently it is of two types. One is a smart home, another one is a healthcare, medical wearables. The medical wearables. So my watch may have a pulse monitor. My watch may have a BP monitor. Most of the heart patients wear a pacemaker. Most of the diabetic patients wear a insulin injector in their arms. And most of the people now, most of the shoes, the jogging shoes or sports shoes come with a lot of sensors. Shoes comes with a lot of electronic sensors, and again we wear a lot of things which is health related aspects. These are all health wearables, or this is a health wearable basically. And again there is another thing, something we called as smart homes. Smart home automation is a very famous application where most of our students do as their final year project. And again, at least 10% of our university projects, final year UG projects, are on home automation. I will come back to the home automation. My comments on home automation later. But the healthcare, medical healthcare is a one consumer IoT. Smart home is a consumer IoT, and Internet of Vehicles. This is not the in real Internet of Vehicles. It's a something. It's an Internet of Vehicles for. It's an Internet of Vehicles for infotainment. For example, I have a GPS, I have a map, Google Map using in the vehicles, and vehicle data sharing. Something like this. Coordination between the vehicles is also a part of a consumer IoT, which is not at substantiated fully and not at clear, technologically not very clear. But when it comes to the consumer IoT, two sectors, that is a medical wearables where the individual person will wear a lot of things on his body, sensors, etc., and smart homes or home automation. But there are the problems here. The medical wearable market is fine. Any research in medical wearables and its their security aspects, all these are welcome. But the smart home or home automation is a very tricky, sloppy, and very uh, and not a very successful venture. I see the most of the startups with home automation or a smart home related products and service will go bankrupt very easily, because even in advanced countries like America and Europe, people doesn't like smart home products. The smart home products. Most of the smart home products are not encouraged, and initially they get a lot of boom. It's fantastic. It's great. Everything is fine. But even though the people who buy it, they will abandon it within 15 days or 1 month. The simple reason is psychology of a customer. The case is the psychology of a customer is like this. For example, let me take myself. I will put an alarm at 6 o'clock. Do I get up at 6 o'clock? 100% or 99% no. Thing is, I will snooze it. Then I will snooze it. Then again, after 15 minutes at 6:30, again alarm will buzz. Then then I will get up at 6:30. So even if I put an alarm at 6, I may get up at 6:15 and 6:30. The most of us are like this. Most of the human beings are like this. We put a 6 o'clock alarm to get up in the morning, but we get up at 6:15 or 6:30 or 6:45 sometimes. The case is the same. Smart home applications will bring a discipline, actually. Will try to bring a discipline in the life of a home automation in one or the other way. That's where exactly the human being doesn't like intervention of machines in the human life. That's where exactly the smart home related startups, smart home automation related startups will end up as a UG project 8th semester project, not as a, most of the startups will go bankrupt because the people doesn't like it in reality. Okay, that another case I will tell. Another example for the failure of a smart home related automation when it comes to the consumer IoT category is that for example, I am sitting with my boss. I am in a serious discussion in the evening 5:30 before leaving to the home, or 4:30 in the afternoon, or 4 o'clock or 5 o'clock after a hectic day. I am sitting with my boss in a serious discussion. And suddenly a message will come on your mobile phone that LPG cylinder will get over in another 1 day. Please book it now. We will get irritated. We will get seriously irritated on this aspect. We will get serious. We will get seriously irritated if I'm if I'm so the case is we get seriously irritated. This I'm just taking two examples. One is alarm, which is we means why the alarm example is that we are not disciplined. We don't like to getting disciplined more. Okay, we are disciplined, but strengthen discipline we don't like. That's one part. The other part is this type of nuisance they create. In serious meeting, they get a message that LPG is getting over and again you have to book it now. So this type of messages and all are useful, seems useful, but they get irritated at a particular time or something like that. This may be not very serious examples, but these are somewhat a sensible examples. Where exactly the psychology of a human being, understandings of psychology of human being is very important in the success of a home automation product, especially in the consumer IoT segment. Fine. When it comes to the healthcare related stuff, the one very important stuff is that it affects the consumer's comfort, security, and efficiency. Where exactly the comfort? If you wear something on, for example, the insulin injection machine, generally we wear in the arms, below the arms, is a very uncomfortable thing initially. Until unless we get habituated to it, the device and the insulin tank and all is a very uncomfortable thing for any human being. And again, you can just in when I was a hardware security researcher long back in 2013-14, I read about one news when Obama was a president. The current president was a vice president then, Joe Biden. Joe Biden is a cardiac patient, and again he wears a pacemaker, consumer IoT. But somebody hacked his pacemaker. Somebody hacked his pacemaker because the pacemaker was connected to the internet, and Biden's personal doctor used to monitor his heart and its pacemaker working very oftenly in a day, 2-3 times a day, 5 times a day. And again, he saw the pacemaker behaving very peculiarly. The doctor observed the pacemaker behaving peculiarly. Then suddenly he called Biden, and again he said, disconnect the internet of pacemaker because somebody is hacking your pacemaker. Means this came in the news. I don't know the truth of this news, but I read this news during 2013-14 when I was a PhD student at NIT-Rourkela. Exactly this kind of stuffs are all a motivation for our hardware security research during those times. So this is all exactly the security of IoT. The security of IoT is a question point. Is a point where exactly the consumer IoT, the data security, hacker security is all exactly, it may kill a person. A consumer IoT, a medical wearable might kill a person, might harm a person in a very bad way. So we have to be very careful in consumer IoT when it comes to security. So this is with respect to the consumer IoT, what I have. But most of the other consumer IoTs are not very matured enough. For example, Internet of Vehicles, or else some other examples. Somebody will we can do who can get it. So the other most important IoT today is for example, is the industrial IoT. This is where exactly the money is there. Where exactly the money is there. According to the survey, the industrial IoT could add a $14.2 trillion to the global economy by 2025. Currently, for example, if you name a few companies, there are a lot of companies, including Honeywell, etc., etc., etc. But there are a lot of companies which Siemens and GE are the two major industries, primarily focusing on industrial IoT, and both solutions involve cloud as a data processing platform to connect, relay, store, process, and analyze sensor data. To analyze sensor data. So the Siemens and GE are the two major companies, along with many other are there. For example, Honeywell and all. What exactly these doing? For example, there is a company called as a GE Digital. What exactly they provide? They provide a solution. It includes a complete digitization solution, a complete IoT solution with a cloud, with a gateway, with a edge platform, and monitoring your factory. They completely change your factory. They completely change your functioning of the factory. They create a lot of something called as a digital twins, which we will discuss when it comes to the offline class in the second week or the first week of December. The digital twins, we will have a discussion on that, and it's a security of a digital twins, etc. and all. So basically, they will create a complete digitization of our factory, where we call it as an industry 4.0, where it includes a digitization, a self-organizing automation, a predictive maintenance, and which are essential for the future efficient production process and manufacturing operations of smart factories is done in this industry 4.0 or industrial IoT, where exactly most of the startups, most of the IoT startups in this domain, industrial IoT domain, are highly successful. Out of 10, 8 are successful, and means until unless they don't do the serious mistake, they are successful here. They are successful here. What exactly we are doing here? What exactly this industrial IoT or industry 4.0 means? For example, let's take a simple examples like a generator which generates a diesel generator which produces electricity, a motor which is used in our homes to pump the water from a sump to the overhead tank. These are general common things we use in our day-to-day life. A motor, a generator, like the kind of stuff. For example, in this motor and a generator, why can't we have one microcontroller board inserted in that to monitor the health of a generator and to monitor the health of a motor? Health of a motor means every 15 minutes, it collects the data collected with the functioning of a motor. It collects the data. Let's take one microcontroller board, connected to the internet permanently with a battery operated board, which collects the data connected with the motor, whether how much time the motor is on, whether the motor is functioning smoothly, is any complete health care of motor is collected by the sensors very oftenly, and that will be sent to the cloud. When anything happens there, if the motor is in AMC, immediately by looking at the health, immediately a service engineer will come and inform us that your motor will go bad in 1 or 2 days. I will repair it. We have a data with that. Or else we are collecting a data from every motor we produce and we sell. We can say to the manufacturer that in the manufacturing process, we can say that this batch of motors has got this problem. We have to correct it during manufacturing. Or else this batch of generators has got this type of problem. This batch of generators has got this type of problem. So we have to be very serious about this. We have to be very serious about this. Some mistake is happening during, either it's a design problem or a manufacturing problem, we have to take care. So we have a data. We have a data on every product we sell to the customer. We are monitoring its health every 15 minutes. We are collecting data of that particular generator or a motor every 15 minutes. We are analyzing the data, and we know what exactly we are doing. This is exactly the digitization, what the digitization means. Then again, the self-organizing automation. What do you mean by a self-organizing automation means? For a given, based on the inventory stock, a CNC lathe will take a call that what production should occur, what needs to be done, etc. And it's based on the situation, based on the factory system, what is happening in the factory. Your complete factory will get reorganized or restructured for the requirement. So we need to produce a bolt birds or nuts. So we have to reorganize in such a way that this is how we need to work. So this is a self-organizing automation in a very gross level or a very basic level. Then the predictive maintenance. The predictive maintenance means it is very similar to the generator and motor. We collect data. Obviously, we will do the not only the digitization of the data. We are doing a predict. We can do the predictive maintenance using that particular case. This the problem is we are all talking about this predictive maintenance, digitization, self-organizing automation. When it comes to the research, we have a problem, especially in the academic institutes. We have a serious problems in this area. We are all fascinated about the industry 4.0. We want to work in this area, but we have hiccups. What are the hiccups? The first thing is we don't have a data. From where I will get the data to do the big data analytics or to do the data analysis? That's one part. Or else, how can I design the edge node to collect the data? Okay, if I do the edge node collection, that becomes an embedded system design. If I do it very well, it becomes a master's project, not a PhD project. Exactly, this is where exactly the problems are there. We don't have a data with the where the industry has got the data. We don't have an access to it. At the same time, if we design a edge node or a gateway for that one, that becomes a classical, very good embedded system project, but not a PhD problem. This is basically the where exactly the finding a right problem in the industry 4.0 is a very challenging thing for any researcher today in academics, until unless we bring in the security aspect here. Until unless we bring the security aspect here, we can get enormous problems. Here we will put a one crypto, there we will crypto crypto, here we will bring the hardware security concepts. Then the PhD problem will become easy. Without bringing in the security problem, if I want to do only the industry 4.0 application level, barring this security, especially in the digitization, self-organizing automation and predictive maintenance, either we don't have data, even if you design an edge node, that becomes a classical MTech project, not a PhD project. So here exactly we have to be very careful. While we don't want to do security because everybody is doing it, but I want to do in the industry 4.0. We have to be very careful here in choosing the research project here. So then next we come to the next point, that is called as commercial IoT. Where exactly the last version of our IoT, that is commercial IoT. These commercial IoTs are very similar to the IoTs, but in complex in terms of nodes and number of people served. These commercial IoTs are solutions for huge shopping complexes, malls, hospitals, and all. These are all basically where the commercial IoTs we can deploy it for the smooth functioning, security, surveillance, safety, people movement, reliability, working of escalators, etc., can be are the commercial IoT problems basically. But here, this category of IoTs are highly customized for the particular mall, hospital, and any other similar large size organization, exhibition, museum. Then we can do some amount of commercial IoT in this case. This category of IoTs are highly customized for the end customer requirement in comparison to the consumer IoT and industrial IoT. A classical examples are IoTs in big shopping malls, hospitals. But one other important commercial IoT is agriculture IoT. We can see a good number of agriculture IoTs in the market, and also there are a lot of startups in this area. And a big amount of startups are there in this area, especially in agriculture IoT. They bring a lot of deploying, in a lot of areas. There are a lot of things from large scale to the small scale, and there's a lot of big data companies in agriculture marketing, etc. But the basic problem here is, does they work for the Indian conditions? Does they work for the Indian conditions to succeed in India? If it is a startup, the basic problem with this agriculture IoT is in the world, the least mechanized agriculture system in the world is India. Australia is highly mechanized agriculture. US has got a very highly mechanized agriculture. European countries have got moderate mechanization in agriculture, but India still follows the primitive 2000 years old mechanisms in the agriculture. The simple reason why we have this problem is the landholding size. The landholding size of agricultural land in India is very less. That is 2.5 acres. But in Australia, it is 5,000 acres. In USA, it is 700 to 800 acres. In Europe, it is much more than 100, 200 acres. Average land holding, where we can bring in the mechanizations and agriculture IoTs very well in Europe, Australia, and America, but not in India. Because you can going for an automation for 2.5 acres of land or 3 acres of land does not, it will be a huge investment with minimum returns, or else the landowner or a farmer doesn't have a financial capability to implement the agriculture IoT in his this one. And again, there are a lot of operational problems that we don't have a road to the farmland. We have to go by other farmlands. Wiring, there are a lot of operational problems will be there. Somebody designs an IoT projects, agriculture IoT solutions, from harvesting to the crop protection, etc., for the Indian conditions. That is, the land holding is very minimal, 3 acres of land or 5 acres of land. In this case, that will be a successful IoT. But there are a lot of IoTs. There is a lot of effort in this area, but there is a minimum penetration of technology in agriculture when compared to the other areas of IoT, because the awareness, financial capability, and the inherent or native motivation for mechanization of farm is not there. So that's where exactly these are the various two different types of IoTs in commercial side, that is agriculture IoT and shopping malls, hospitals, museums, exhibitions will make a where exactly we need a commercial IoTs. If you have any questions connected with this is a taxonomy of IoTs. This is a broad taxonomy and categorization of IoTs based on the application. Because why I am saying in IoT is what? How it is different from embedded system and CPS. Where how to categorize the applications of IoT, how to look at into IoTs. This is what I was intended to cover, and I hope I have covered. If you have any questions, I am ready to take. Means questions from my participants. Any questions from the participants? No questions. We will continue. We will continue for another 1 or 2 minutes, and we'll take a break for a few minutes. So next comes to the data analytics connected with the IoT. We collect large amount of data. Means large amount means it's a seriously large, seriously big. For example, the very recent project which I did for Bangalore city, that is a smart traffic monitoring system, where we log 70,000 violations per day. We have implemented only 50 junctions. We have implemented automatic number plate recognition cameras, red light violation detection cameras, and again we have installed 6 to 7 cameras or 5 to 6 cameras in each junction, depending upon the how the junction is organized or how the junction roads are designed and all. Based on the location of the junction and all, we installed 5 to 6 cameras. Maximum are automatic number plate recognition on this type of cameras, and red light violation detection cameras which look into the overall junction. In this we are collecting a data of 7 violations or 6 violations basically. One is no helmet, triple riding, over speed, no seat belt, then seat belt, driver on call, and red light violation, stop line violation. All these things we have detected. In Bangalore city, with 50 junctions installed, we are logging 70,000 violations per day. 70,000 violations per day. You can imagine for each violation, we are logging a 20 seconds video, 3 to 4 snapshots. You can imagine what is the amount of terabytes we are storing every day for the violation detection. It's a seriously high. And again, imagine if you are logging a 70,000 violations, if you are logging a 70,000 violations in the Bangalore city means I'm saying, it's not an exaggeration. It's a working system today. It's a practical system which I worked from last 1 year. Traffic commissioner, and we have installed the system successfully. And there's no exaggeration. We are logging 60 to 70,000 violations per day. All these 7 violations, without any exaggeration. It's a real numbers. No, it's a real numbers. I can show the videos at the end of the lecture. I can show few videos which we have collected for quality check and other related activity and all. The problem is, if you have a 70,000 violations are getting collected, then somebody has to sit and print a challan for them. Go check it, whether it's a real violation, no helmet is really there, confirm it, you ensure that proofs are there, then print a challan and post it to the people who has violated the traffic rules, no helmet or triple riding or whatever it is. How many people do you deploy? How many police constable you will deploy to analyze the 70,000 violations? It is impossible to recruit to people. You have to recruit minimum 1,000 to 5,000 people to analyze 70,000 violations per day. The only thing is we get into the feature called as an auto push or auto valid. We just check it, apply a machine learning algorithm or artificial intelligence. If any detection comes, no element detection comes. How much confident it is? Means we will ask the system itself how much confident you are. Are you 95% confident that it's a no element detection is 95% confident or 99% confident? Then print a challan. If you are 85% confident or 80% confident, keep it aside. Then again, after 5 days, just check it again with 95% confident that still it is all the 95% confidence or 90% and above confidence, just print the challan without any manual verification. Anything below 90% or 80%, a manual verification is required. Now, for example, if I have 1,000 no helmet violations per day, let's take an example. We get out of 70,000, we are getting around 10 to 13,000 no helmet violations per day. Out of 70,000 or 68,000 or 65,000, we are getting 10,000 on an average no helmet violations per day in the Bangalore city with 50 junctions collected data. In that one, 3,000 to 4,000 are going for a auto valid, that is no manual verification. It gets channel get printed, but another 6 to 7,000 violations needs a manual verification. So still we need a lot of manpower. So what exactly is happening is we now the machine learning algorithm or the AI algorithm is running on that application. It will learn the pattern. It will learn the violation pattern gradually in next coming 3 months, 6 months. In the coming next 3 months, 6 months, and 9 months down the line, this auto valid now it is out of 10,000 no helmet violations, we are getting 3,000 violations going for auto valid. Maybe it will increase to 5,000, 6,000, 7,000. Very minimum out of 100 violations, 80% should go for an auto valid, 20% should go for a manual verification where that can be done manually. So where exactly we amount of data, a manual verification, manual crunching, or the Excel-based crunching, normal Excel macro crunching is not possible. We have to employ AI ML algorithms to crunch the data and to get the meaningful insights into the operation of the environment of a system. So with the IoT sensor data gathered through multiple devices, a data analytics will yield greater insights into the operation and situation of environment or a system, providing a more accurate understanding of conditions and status. Hence, we can do fine tuning. That is exactly that. Now, with the amount of data we are getting into the traffic management system, slowly we use that data and we'll train the AI ML algorithm to detect confidently more violations. And again, we have to improve that auto valid feature that Out of 100, 80 will get automated channel printing. No manual verification is required. That is exactly the fine tuning is exactly. The faster response, efficient operation, greater safety and automation. So this is where exactly the sensor data gathering takes time and different frequencies to gather, and some applications demand real-time analytics, especially in the financial markets, stock trading, stock market apps, or else something related to the petro pricing, crude oil pricing, or the something related to the warfare, real-time warfare, or cyber warfare. All these needs a real-time analytics, real-time data analytics needs to be done. And data analysis a large amount of data needs to be analyzed at a very faster rate, and also decisions should be taken faster. That's the reason the why this real-time data analytics has changed the economies, actually economic thinking also. We see the chief economic advisors to the governments across the world. We see they're talking about high frequency data. What is this high frequency data? That is, which is not available in the earlier days. Now through various means they are able to gather high frequency data. That is, every day, every half a day they gather data: how much cement consumed, how much electricity consumed, how much iron and steel was consumed, and all. Based on this high frequency data, they come up with a new conclusions on economy of a country, etc. So this is called as an high frequency data analysis, which is a very hot area of research, basically. Very hot area of research. And again, designing an hardware accelerators for high frequency data analysis is a very lucrative research area, where we can employ hardware accelerators and FPGA devices to achieve the high frequency data analysis. High frequency data analysis on FPGAs is a very attractive research area. So this is all about the data analytics connected to the IoT. Next, we will come to the IoT architecture and protocols, because I'm already these things are covered in the last 2 days. I don't want to repeat. It's just one slide. So next, we will go to the a gross comparison of features. Before going to this, we'll take it back. Nowadays, in my watch, it is 8 o'clock, 7 minutes. 8 o'clock, 7 minutes in my watch. Let's come back at 8 o'clock, 15 minutes. Exactly at 8:15, we'll come back and we'll start we'll start the class again. We'll take a break for 7 minutes. Thank you very much. If you have any questions, I can take in the break time. Also, I can take a questions in the break time. I am available. Okay, fine. We are back. So let's continue the lecture what we have discussed. So we'll come back to the structure of IoT in this particular thing, the world of IoT in a minute. Before that, we can still analyze on the IoT features and its comparison. That is, how do you means, for example, if you are not considering the community IoTs, because community IoTs belongs to the community, and again they are the very primitive IoT solutions. So we consider it as belongs to the community. But when it comes to when you are making a consumer IoT or an industrial IoT, consumer IoT, the impact is, how do you impact the consumer IoT revolutions? Industrial IoT is an evolution, means it slowly, actually initially everybody, if you ask in the 2014 or 2015, if you ask and name a few IoT application, the first thing which will come to everyone's mind was home automation or smart cities, smart this one. But now that digitization, predictive maintenance, this evolved. Actually, it got evolved after 2016, 17, 18. Slowly, the industrial IoT or the term industry 4.0 got evolved. But the consumer IoT is a revolution because there was no. It was just a watch. Now it became a smartwatch. Earlier it was it was a pacemaker. Now it's a smart pacemaker. So it's a revolution in the terms of consumer IoT. But in industrial IoT, gradually after a lot of mistakes, gradually it evolved. And in consumer IoT, it's a service model is a human centric, and industrial IoT it's a machine centric. And in service model, the human being is primary in consumer, and industries the machine is important. The status is new devices and standards are coming up in consumer IoT. In industrial IoT, we have to adapt to the existing system. We have to understand the existing devices. We have to make them smart in one or the other way. We have to existing standards. Industry standards. We have to understand. We have to fine tune the standards to the industrial IoT, because outright removing a factory and establishing a new factory with IoT is not possible. That is highly capital intensive. The next is connectivity. In a consumer IoT, I can connect, I can disconnect. But in industrial IoT, it's a structured, centralized network. We cannot play around the industrial IoT. Criticality is in North tendency, excluding few medical applications like pacemaker and insulin tank. And in industrial IoT, it's a mission critical and it's very tough. And the data volume is in consumer IoT is medium to high. In industrial IoT, it is high to very high data is getting generated. So the next is the industrial IoT architecture. Industrial IoT architecture. The industrial IoT architecture is whatever we have shown in the diagram is the first we start with the primary element, as we already know in the last 2 days you might be knowing this. So here exactly we have a sensors and actuators where microcontrollers stand, and again we have a gateways, basically the Wi-Fi gateways, Zigbee, LoRa, MQTT, all this networking stuff came, which we have already discussed in the last 2 days. And again finally we have a enterprise analytics at the cloud level, a standard industrial IoT architecture, which I don't want to go much deep because already discussed. The next, what are the research problems in IoT? Apart from this industrial IoT, I said in the consumer IoT means in IoT without mixing security, research is difficult in all segments of IoT. A simple reason is either we don't have a data. If we do the edge nodes and the middleware, it becomes a classical MTech project and not exactly what we don't had any much value in the research. But still, there are a lot of areas of research in both IoTs in VLSI and embedded systems. One, data interoperability. This data interoperability is where exactly that we can do the research. billions of heterogeneous devices, a lot of billions of devices or millions of devices, or at least thousands of devices, hundreds of devices. Let's not exaggerate. I don't see any IoT system with billions of nodes today. Generally, it is in thousands, in lakhs is also very rare. Very rare, especially in automotive segment. We might get millions of nodes in the future, but till now it is not yet happened. Till now it has not yet created. So the billions of devices generate a disparate data with their own formats. A data transmitted from processor to gateways and cloud servers should use the same data format, which is understood across a different IoT layers. The standards for data interoperability is still an open problem. Is still an open research problem in IoT, where the people can focus. We can develop a data standards. We can develop a data standards, and we can test the data standards on their latencies, on their compatibility. We can compare, we can produce, we can add a value in this area where data interoperability is there. The next is the low power device support. Now, most of the IoT devices are low power and battery operated. We have to choose a low power microcontroller. We have to develop a low power PCBs. We have to develop overall low power systems from the VLSI chip level to the embedded system level to the PCB to the cloud connectivity. So here exactly the choosing the components to design an edge node is very important. The microcontroller as a SoC used in the edge node must support internet connectivity. The internet connection is not optimized for low power consumption. It consumes very high power. And also the cryptography for security purpose, whatever we use, is also consumes a high power because the cryptography is a computational intensive problem where we have a lot of power get consumed. So we can look out for an options like lightweight cryptography, lightweight ciphers for the low power achievement to achieve the low power, and also we can optimize how to optimize the internet connection, how to optimize for low power internet, how to get the low power internet. So this is exactly the we have to choose the right configuration of networking. Means initially I will choose Zigbee, I will transfer it to the nearby gateway. That gateway is powered by the grid. From the grid it gets connected to the internet, etc. and all will be the internet connection is not optimized, but we have to think the in a different networking architectures must be devised to achieve the low power IoT application. The next is the power management in the IoT edge node devices is crucial. For example, I have a battery operated a sensor node, a water pollution monitoring sensor node in the middle of the lake. I have installed it in the middle of the lake. I have installed the water pollution monitoring sensor. There exactly, what is this power management? That power, I cannot very often, I cannot go there and change the battery very often. We have to choose a power management circuits, especially the IoT edge node power supply design. It's a very active area of research. We have to install the solar power there. We have to have a battery charging mechanisms there. IoT edge node itself is of my palm size. IoT edge node itself is a very small device. It's a very small PCB, and also it's a very small device. In that we have to get the some solar charging mechanism there, and also we need to have an ICs, and also we have to design a system there to charge the battery in the middle of the lake. So that is where exactly the research problem is there. Power management for the IoT edge node is crucial because the edge nodes are dispersed across different geographies and different terrains like middle of the water, deep inside the forest, in top of the tower, in top of the building. In all difficult situations, edge nodes are deployed where exactly the power management, renewable energy, that is using a solar plates and charging the battery is very important. And designing a power management circuits, PMIC circuits for IoT edge node is still a very good research problem where somebody can focus on. Designing an edge device with the low power components without affecting the performance is a challenge for designers. And also we have to design chips for PMIC chips for IoT edge node. The next another most important thing which we discuss is security and privacy. In complex ecosystem, at any stage, there can be a malicious hardware or a software which compromise security. It is very critical to ensure the data security and system security, which is a multidimensional research problem. We'll take up in the upcoming slides in a more detail. So the next another important research problem in IoT is product development and manufacturing. So this is a one type of not only the ECE problem or a computer science problem. It gets into the mechatronics in more of the in most of the situations. But product development and manufacturing is highly diversified in IoT ecosystem due to the large number of applications coming under IoT umbrella, a number of IoT hardware, the edge devices and gateways and manufacturers. A lack of standards in the IoT edge device and gateway design will create a compatibility issues across the manufacturers in the future. So this needs a lot of regulations in terms of manufacturing, product development, and a lot of standards needs to be followed in the, and again who will develop the standard, who will develop the regulations. Again, the researchers has to work on regulations and standards, available IoT standards, regulations, data protection bill, etc., and all, to follow the design and the gateways. And developing standards and regulatory mechanisms needs a serious research, which is an open research problem. Somebody can pursue a PhD in that. The next, already we presented the importance of analytics by taking a smart traffic management system, which we have deployed, which I was involved in deployment and designing and deployment of that system. Now the data mining and crunching is a crucial component in IoT ecosystem. Ecosystem to extract the meaningful information from raw data generated and different sensors and data collected from various sources, including social media. Handling different patterns of data is a unique challenge in IoT. So I don't know what are the data formats I will get, whether I want to do the sorting, I want to do the merging, I want to do the merge sort, whether it is a queue form. I don't know what exactly we have to do. There is no standard source of data, and there is no standard way of crunching the data. For example, if it is a data connected with the vegetables market, then the data formats are different. The what data we will get is a different, but this standardization of the data crunching, extracting the meaningful information out of data crunching across different industries is not a common problem. Is not a common thing, and it's an open research problem. We have to devise a unique solutions for a unique situations, which is again we need a standards there, regulations there, exactly what we don't know what exactly we have to do. This is where exactly the big data analytics and how do you hardware accelerate the big data analytics. Based on the concept, based on this, because to address this data analytics problem, there is a lot of things came like fog computing, mist computing, etc. All are being developed. Based on this concept, the fog computing technique is developed and discussed widely in IoT literature, where the traditional data mining algorithm suitable for centralized computing infrastructure does not fit into the IoT. Because we cannot do that, so we will distribute the computing across the different IoT edge nodes. In gateways, we will crunch the data. We will get the data already a partially processed or semi-processed data to the server. Then we will get the job done. There is a need to develop a novel algorithms for data analytics which support fog computing, mist computing, and modern IoT requirements. And also we have to make it low power, high performance. And also we have to make architectures for that. That is an open research challenge when it comes to the data analytics and IoT. Further, a critical challenge is to decide how much data to collect, aggregation of data of different edge nodes, router design, gateway design, and finally the cloud computing is an open research problem. So these are the few computing things which we may be looking in, and also we have to do a deep research in these areas to figure out the problems to the analytics acceleration, analytics acceleration, data analytics acceleration, and data analytics in IoT, how we can best use of the resources for computing and analyzing the and data crunching. So next, which comes to the real thing of today's talk, or today's theme of the FDP, that is factors affecting the security of IoT. The one is the scalability. The major challenge for security is the scale, diversity, and customization. IoT system will have billions of devices connected in the network. Designing holistic data and system security using generic cryptographic techniques for a large system is difficult. For example, the very initial IoT application like Barcelona Smart City project has got a 75,000 sensors. The next is diversity. So the scaling, that means if it's 75,000 sensors in Barcelona, Bangalore may need 75 lakh sensors or 75 crore sensors. So the Barcelona is very small when compared to the Bangalore. So the case is we have a scalability is a problem. The scalability is a problem. We have to ensure that connecting an IoT edge node and removing the IoT edge node does not create a serious problems. And also the cryptographic techniques. If we have a device authentication, device identifiers, and all needs to be clearly managed for the scalability issues. Then the diversity. The diversity of IoT edge node device platforms and gateways make a generic security design challenging. We don't have a different IoT edge nodes are there. For example, the sensors or sensor board or a sensor interfacing circuits for air pollution are different, water pollution are different. Obviously, we have a cameras in smart transport. The camera data is an image, and temperature data is a voltage signal. Water pollution data is in a different format. So exactly the diverse data or the diversity in the edge node design, and again each will produce the data in their own way. Each will produce the data in their own way. The customer security architecture is deployed because their manufacturers are also different. A customer is even we face actually when very recently when I visited very recently means yesterday only when I visited a S2P IoT open lab in Bangalore in Electronic City. The issue is each guy is devising their sensor nodes, sensor networks, or the edge devices in their own way. One needs a battery of 3 volts, another needs a battery of 5 volts, another one needs a battery of 2 volts. Crazy thing. So this is basically there are very practical difficulties because of the diversity. I'm just saying a power supply diversity. Then there is a interfacing diversity. Means GPIOs are not enough on that particular board so that can be connected to the other board for fog computing or the mist computing. So basically there needs to be, because the guy who produces a software for IoT edge nodes is different. The guy who produces a hardware for IoT edge node is a different. Who manufactures the PCB is a different in one or the other way. So a system integrator is different. The guy who purchases software, a guy who purchases hardware from a different source, he integrate that both of them and sell it to the end customer. At the end of the day, system, if any problem occurs, system integrator doesn't know how to manage the scalability or a diversity. This is a basic problem. We see it in the IoT solutions today in most of the applications, especially in the smart city solutions and smart traffic solutions. This is my practical, real experience. Because the system integrators who bid for the project and they get a software from a different place. They get a software from GE or CDAC, but they get a hardware from a different vendors, different single board computer makers, etc., and all, and are different embedded companies, and that doesn't sync at all. For example, in a smart city project, for example, one startup will give a air pollution control, but they don't have a water pollution control software. That we have to depend upon some other guy. And one startup only produces water pollution and air pollution software and hardware, but they don't have a garbage management aspect. We have to look for a garbage management aspect for a different company. This system integrator who takes everything from a different places, integrate them. At the end of the day, it's a junk solution. It looks like working, but in practical deployment, it may not work. So basically, the problem in real deployment is the guy who is producing air pollution one, water pollution solution is not having any solution for the garbage management. The guy who is having garbage management and the air pollution and water pollution control in the IoT project, it doesn't have a parking solution because the parking is an important component in the smart city. You don't have any idea on parking, parking or parking management or anything like that. There is another thing called the entry of vehicle and exit of vehicle management. This again, the image processing will come into the picture. Again, the solutions will go. A system integrator will go mad in integrating everything on this. This is actually a practical diversity problems we face in implementation of smart city or smart transport. Basically, these are all the practical examples we face in the smart city problem, which I faced in different smart cities like Bangalore smart city or Davangere smart city or any other Pondicherry smart city. So this is the real life experience with respect to the scalable. The scalability is a big problem. A diversity is a big problem because the software is given by one. He doesn't have a software for everything. Hardware is given by one. He doesn't have an hardware for everything. And they are not compatible. Hardware, software not compatible. At the end of the day, system integrator will face a major challenge in scalability and diversity. The next is a device life. Next is a device life. In few IoT applications, a device life is very short, and in few applications like automotive device, a device life is very high. For example, car I will use for 20 years. I want a microcontroller in my car to work for 20 years. I will use a mobile only for 3 years or 4 years, I will change my mobile. In the same way, there are a lot of IoT applications where a device life is very short, and there are few places where the device life is very high. So again, the designing a security aspect for a long life device, for a short life device, a security thinkers means I'm not thinking about hardware security, a software security, a system security, and hardware security. All holistically needs to be given a thought. In this case, a security techniques needs to be designed. All the three system. Now hardware security was a standalone problem in the earlier case, but now it has become a problem because just I will come back to the case where exactly we are working with the Intel, where exactly we need to design an BIOS for IoT solutions, which is a new project we are taking up with the Intel. The case is there are a lot of things like TPMs, device identifiers, DICE, that is device identifier, composition engines, and also the firmware needs to be designed for security, and also this TPMs are hardware, device identifier, composition engine, which is a key security component today in most of the IoT devices, is both a hardware software co-design component. And again, there is something called as a UEFI. That is where exactly I will just open for the benefit of the participants. I just open this one, something called as a UEFI. That is Universal Extensible Firmware Interface. This is basically a boot firmware. This is basically is required for the security today. We have to do the extensions to this Unified Extensible Firmware Interface (UEFI). Somebody who is doing an hardware security research can take this UEFI, then they can look into the how to replace this existing UEFI with a secure UEFI. That is again the hardware and software co-design problem. How much of new UEFI should be hardware? How much of new UEFI should be software? So this UEFI was designed in 2006 to replace the BIOS, that is a basic input-output system, boot firmware. So this is basically the problem where we design the IoT needs an extension to this UEFI, to make the secure UEFI for IoT devices. So this UEFI came in to address the BIOS limitations, that is basic BIOS booting hardware limitations. But now UEFI has a limitations because this cannot be deployed for IoT for various reasons. both in security and computationally related problems. So this is basically the problem with the device life, what firmware you will have, what exactly for devices with a long life, what type of security, what type of, there must be an option for security features update through hardware, software. This booting UEFI related, lot of things are happening. DICE, TPM and all needs to be taken care for long life, for a short life. And again, the update feature must be there for a long life one. A short life one, we need to have a stringent one, because the short life IoT devices are more vulnerable than a long life devices, because long life devices are used in avionics, automotive and all. A short life devices are used in smart city or a smart transport, or not smart transport, it's a smart city solutions and other applications like healthcare, the consumer IoTs and all, where we need a stringent. Uh, the security aspect is different in the case of a long life IoT device and short life IoT device. The next another thing is, the crazy thing is, most of the researchers, students, UG students, PG students, and researchers will download a lot of code from a GitHub. They will deploy, they finish their project. But this is one of the major security problem, and also not a good thing to do. This we call it as, in our terms, we call it as a jugaad. Doing jugaad with downloading systems from GitHub is a very bad thing to do in some places. Open source software is widely used in IoT systems. The usage of open source programs is advantageous for quick development of IoT devices, but developers should carefully choose their software. Excuse me. Just a second. So this is the open source system. We have to be very carefully, and there may be a malicious content, and we have to very ensure that there is no malicious software, malicious Verilog code, or a malicious system C code there, and we have to very ensure that particular process. Then again, the software or firmware upgradation. Most of the updates we do through Google Store. It's an online update. For example, a traffic light signal, a traffic light timer needs an update. How do you do it? Climb the pole, remove the system, take the JTAG, then download the new code. That was before 2015. Now it's an online update. Through online, through internet connection, we are updating. So this is a very good thing, but also a vulnerable thing. A hacker can hack a network and upload the system with his own over-the-air update supported by cloud. Updated distribution can be done by a centralized infrastructure without much user involvement. This creates a real serious problem where we have to, in this case, the security challenge is of two types. A proper authentication and identification of the edge device in the network of billions, and to make sure no malicious drivers or software is not installed on edge devices in the name of updates and upgrades. If we have a malicious upgrade on a traffic light signal, the next is the cloud data center. All commercial activity in the IoT is supported with the cloud-based data storage infrastructure. The cloud is an integral part of IoT ecosystem and enables most of the services. The cloud security and IoT edge device security are mutually dependent factors. That is what the security is. The one link in the chain is weak, then security is weak. In designing security, we have to look into the complete ecosystem more holistically across different hierarchies, from cloud to the final edge device, to ensure there is no compromise in security at any layer. The next is authentication and pairing. The large number of devices in the IoT network complicates the pairing of devices. A pairing is required to aggregate and segregate the data generated from the edge nodes. It is important to make pairing process secure. The adversary can tamper with the data and node identification credentials. Basically, the physical and clonable functions and other hardware security primitives are the solutions, but getting the interface between the puff and software is a credible challenge today. Means it's a credible, a potential research problem at the industrial level. The researchers can put a puff-based solution, but the reliability is a big question in the industrial structure. Very recently, when I visited IESA, the basic problem when I propose a puff as a solution for authentication and device identification, a very fundamental problem is the reliability of a reliability is a problem. The Maxim's integrated circuits, the Maxim company has a puff device actually. The Maxim has a puff device of its own. They say that it's reasonably reliable. The Maxim integrated circuits, the puff product is there. They call it as a chip DNA, embedded security puff technology. People say that this particular physical and clonable function can be the most reliable thing. Means I'm not marketing the Maxim here. I'm just giving an information here. This particular chip DNA works very well. They call it as some number, a DS, DS28E50, a DS28E50. So this is basically a puff structure. Generally, the commercial puff-based solutions are using. They say that this is reasonably working. This is reasonably working at the commercial level, but still we have to see the deployment and penetration of puff technology in identification of a device, identification of an IoT device, and identification and authentication of IoT device is still in the very nascent stage. It's still in the very nascent. Somebody want to use a puff in real time. You don't want to design a puff in FPGA. I want to use a puff in my embedded system project. Better you buy a Maxim product and use the puff in your solution and just check how the puff chips were not available. If you want to use a puff, you are supposed to use it in a FPGA, create a puff in FPGA and use it for device authentication or a system identification, etc., hardware security driven authentication. Now you can use a puff from the Maxim or any other company because I know this Maxim is the most reliable, what the people say, the users saying. So you can use a puff from this company and again use it for authentication or a pairing purpose for the better embedded system design or a better IoT edge node design. So the next is when it comes to the real security problems now, there is the vulnerabilities of the IoT edge devices and the perception layer. We call the edge node also called as a perception layer. So the edge node devices collect the data from sensors and control the physical components of a system. There are few, I just list out the normal attacks which are available in the literature, but each attacks can be a multi-level attacks. There can be a new attacks in the recent times, but grossly I try to comprehensively I present the different type of attacks that can be each research problem now. Multi-level attacks is a trend today. The mixing of these attacks, multi-level attacks is a trend, but still there are few attacks like node capture attacks. An adversary will capture the node or replace the entire node or tamper the hardware device. A confidential information like crypto keys, access keys, and other digital rights managements are exposed in the node capture attacks. So what is this node capture attack means? We deploy the node in the deep forest to identify a tiger, to capture the tiger movement, or the deep inside in the middle of the water, in the middle of a lake, I will install an edge node, or in the middle of a road in a traffic. So if I installing the devices at the very remote terrain in the remote places, obviously the adversary will get hold of it because you cannot deploy a security person for each edge node. We have hundreds, lakhs of thousands of edge nodes. we have a thousands of edge nodes. We cannot have deploy a security person for each edge node. But edge nodes are generally deployed in a very tough terrain and unsecure terrain. An adversary can easily get an access to the edge node and he can hack it. He can, through JTAG or through some other mechanism, he can get an access to the cryptographic keys, access keys, and he can misuse the code. Misuse the node or destroy the node or something like that. A malicious code injection attack, an adversary will inject the malicious code into the memory of the node using debug modules of the node. This happens mainly firmware or a software upgradation through OT. The next is the false data injection attack. An adversary can pump erroneous data through tampering node, which lead to the malicious events in delivery of services to end customer or end user. So, maybe also it cause a service attack. So, the false data injection is again creating a 1/0 type of fault attack, or disturbing the clock or disturbing the power supply will also fall in a overall a false data injection attack basically. By disturbing the clock, disturbing the power supply, reducing the power supply by half, or reducing the varying the clock frequency will lead to the false data injection attack. Or they can put a 1/0 type of situation, and the system will hang, will create a denial of service attack. Then again, the sleep deprivation attack, where the battery will get discharged immediately. Simply we just create an attack which drain out your battery, or else put the malicious code in the memory so that the infinite loops will run and drain out the battery. Then again, the most important thing is this booting vulnerabilities. The rest, all the points which I mentioned above, are can be addressed in one or the other way. The booting vulnerability is very serious. Good evening, madam. Madam ಕಳಿಸ್ತೀನಿ ಮೇಡಮ್. ಆಕ್ಚುಲಿ ಕ್ಲಾಸ್ ಇತ್ತು, ಆಮೇಲೆ ಆಕ್ಚುಲಿ ನಂದು ಇವತ್ತು FDP ನಲ್ಲಿ ಕ್ಲಾಸ್ ಶೆಡ್ಯೂಲ್ ಆಗಿರಲಿಲ್ಲ. ನಂದು ಬರೀ ಆಫ್ಲೈನ್ ಇತ್ತು. ಯಾರೋ ಒಬ್ಬ ಇವರು IIT ಇಂದೋರ್ ಪ್ರೊಫೆಸರ್ ಕೈ ಕೊಟ್ರಂತೆ. Then my professor called me and said, can you take a class from 7 to 9 ಅಂತ ಇವತ್ತು. ಮೇಡಮ್ ಆಕ್ಚುಲಿ 9 ಕ್ಲಾಸ್ ಮುಗಿಯುತ್ತೆ, ಇಮಿಡಿಯೇಟ್ ಆಗಿ ಬರ್ದು ಕಳಿಸ್ತೀನಿ. ಎಸ್ ಮೇಡಮ್, 7 to 9 ಕ್ಲಾಸ್ ಇದೆ. ಅದಕ್ಕೆ ನಾನು ಇವತ್ತು ಬೇಗ ಬಿಟ್ಟೆ, 4 o'clock ಪಂಚ್ ಮಾಡಿ. Then I ran away, means
Sudeendra, you please unmute yourself. Hello, Sudeendra, please unmute yourself.
Yeah, now I have unmuted.
Fine, thank you.
From how long I was muted?
Oh, just 1 minute, 1 minute. No issue.
Okay. The booting vulnerabilities is the one basic problem. Booting vulnerabilities is a basic problem because we can avoid this sleep deprivation attack. We can avoid this fault injection attack or malicious code injection attack, because already we can have a mechanism there. We can already have some security mechanism to avoid the code injection attack or false data injection attack or sleep deprivation attack, because system is running successfully. The system is booted completely. The application is running. Now I have already all security firmware, software or hardware, everything is malicious code injection, everything I can avoid. Somehow I can have a system. But in the booting time, when I restart the mission, or else when I'm switching on the mission, then everything is in a starting process where I don't have any security or antivirus or any security mechanisms, UEFI or anything is not ready, is not booted. I have to boot the system, then I have to invoke the security mechanisms. So before invoking the security mechanisms, during the booting, during the boot process, most of these protection mechanisms are not enabled, and adversary will try to access the sensitive sections of the hardware and software when there is a booting, when during the booting itself, and access to the confidential information, security keys for infection. So the secure booting is important. That is where exactly the UEFI needs to be extended, where the Intel is asking, Intel is seriously looking into the people who can extend their UEFI for the secure booting, where I was involved partially. So there's the hardware exploitation. The adversary can access the debug ports, JTAG, on-chip instruments used for debug and diagnosis, and get an access to the confidential assets. This is securing the JTAG. For example, if my mobile is under attack, just give just I will give my mobile to the service center. He can access my bank password. He has an access to everything. So going deep into the hardware, then you will get an access to the more details of mine. So debug diagnosis equipments, debug and diagnosis ports should not be accessible in a service center. That needs to be only in a authorized OEM or chip makers service center, where exactly they can access the JTAG, they can access the debug or diagnosis port. Debug or a diagnosis port, then we can get any confidential assets to get of the edge device, which are commercially sensitive. IoT designer should choose a microcontroller or a SOC with a suitable debug security features, where it will block the JTAG, debug port, or diagnosis port, so that through this debug channel or a diagnosis channel, he is not accessing the hardware exploitation. He is not accessing to the secure load. An extension to the framework followed in embedded systems, and all types of vulnerabilities applicable to the embedded software are equally applicable to the IoT system also. So the IoT system also. A multi-level attacks using the vulnerabilities in edge devices, gateways, routers. In embedded system, it was a single board.
Your
Now I have
voice is breaking actually.
Okay.
Okay, I don't know. It's maybe for me. Okay, you continue. Maybe
Yeah,
me.
fine.
Okay.
So the software exploitation is where exactly in embedded system we have a one single board. Here we have a multiple places where the software can be compromised. That is the edge devices, gateways, routers, data centers, all software needs to be protected. We need to have an holistic security architecture which includes edge device to cloud to data center working in tight cooperation, especially at the software level, that mitigate the attacks from different places. A router, through router, adversary will enter. He will get an access to the edge device, also gets an access to the data center and cloud infrastructure, where exactly everything is compromised. So at the software level, we need a lot of security. At the hardware level, we need a lot of security. So the holistic security software architecture needs to be placed. It's still an open research problem. So the next, what is the issue here? What is the issue here? That is, most of the IoT literature treats the IoT from the networking perspective till today, and purpose of specific security solutions for a given application or for a given device, which is not generic solution and not incompatible with many aspects when it comes to the practical implementation. So we have few things like something called as a trusted execution module. The security architectures defined for traditional embedded systems are currently used in IoT devices also. The work towards standardizing the security architecture has led to the development of something called as a trusted execution environments long back, 10 years or 12 years back, before the advent of IoT, especially in some specific security applications. Some TEEs were required. The same TEEs are extended to the IoTs today, where these TEEs are tamper resistant, computing environments running a separation kernel. TEE guarantees the authentication of a program code, integrity of a crucial assets of a system like processor registers, program counter, stack pointer, secure memory, etc., and confidentiality of a code and data stored in the persistent memory. Means that a common TEEs are, for example, ARM Trust Zone, Intel Software Guard Extension. Nowadays, they call it as a Intel DICE and all. There is a something called as a Samsung Knox. Now the Samsung Knox, it's equivalent version. They will say that is called as a Google has came up with a new TPM or new TEE called as a Open Titan, which is a new TEE from Google actually. The TEE techniques are discussed to have a more similarities than differences. For example, all TEs are software mechanisms as of today, but TEs must come from hardware. But up to some extent, ARM Trust Zone comes from little bit from hardware, but still 80% is software. Intel Software Guard Extension name itself suggests that it's a software guard extension. So these TEs are, there is a scope for research. The TEs must be redesigned with hardware component and all, where exactly we have a Open Titan from Google, where the maximum component or 50% of the component here is from the hardware. That is something we call as an Open Titan. It's an open source silicon root of trust project actually. Maybe in the offline session or in the future session, if I get an option, I will discuss the TEs in with perspective of Open Titan and also the digital twins and their security aspects. Now, Open Titan is the first open source project building a transparent, high quality reference design and integration guidelines for silicon root of trust chips. Basically, this is a Google project. Basically, this is a very high quality, that means reasonably and a trustworthy silicon can be designed using this. Because the most of the hardware, whatever the TE we are discussing here, that is all corporate TEs like ARM Trust Zone, Intel Samsung Knox, Intel SGX and all. These are 80% or 90% software, 10% hardware. But there the Open Titan is 50% hardware, only 30%, 10% firmware, 40% software, which is a right mix of TE which gets the solutions correctly. The TE techniques discussed above similarities than the differences. All TEs are software mechanisms supported by the hardware like key generation and operating modes. The TEs serve the security issues in traditional embedded systems, but they are not capable to address all the security related aspects of IoT. That's the reason where exactly we need a more hardware based solution to address the security vulnerabilities of IoT, like Open Titan or some other thing may come in the near future. So somebody who is doing a research in hardware security, the best thing is designing a TPM. Start with the Open Titan, understand Open Titan, and get into it. The TEE does not address these TEs, the above listed TEs does not address modern hardware security issues like hardware trojans, unreliable counterfeit parts, and debug security. If you include these aspects into the Open Titan, even still Open Titan does not support any of these aspects. If you get these things in the Open Titan, it's a fantastic PhD thesis, and without any doubt. So the future solutions of TEs should include a PUF, should include a DRM, should include a solutions for hardware Trojan and booting securities, secure boot, etc., etc. And all. This is all about the future solutions. So the future is designing a best TE to address the security problems, and we need to address a lot of other IoT research problems like power management and all. When it comes to the real security, the TEs are the existing solutions. In future, anything may come. A comprehensive solution may be an infrastructure IP core for security, which is implemented in future microcontrollers, which is an advanced versions of current TEs like ARM Trust Zone, Intel SGX. This is a solution to the vulnerabilities of IoTs. Thank you very much. If you have any questions, I am happy to take.
Is there any questions? So I don't think. Okay, Professor Sudeendra, can I ask two question?
Sir, please,
Participants.
sir. Sir, please, sir.
So
Please.
how we can differentiate between this software security and hardware security? It's a basic question. I think maybe it will be helpful for them.
Yes, sir. They actually currently at a very common man level, we have antivirus. And also the
Okay.
email security is that all our web pages has got a AES encryption. Either it is a Internet Explorer or a Google Chrome, they have an inbuilt AES encryption. And so we generally use a software antivirus. This is general security. We have a firewalls at networking infrastructure. And so like this, the stack of security start from a antivirus, then next to the web browsers, then to the gateway firewalls, then the server firewalls. This is a software stack what we really have today. From our basic, the node level, if I'm a laptop, individual laptop, I have a software virus, antivirus. Google Chrome is application has got a AES encryption inbuilt. Then I have a gateway firewall. Then server, we have a lot of firewalls or some other security mechanisms, like access mechanisms, root user, super user, at different levels of activity. But when it comes to this mechanism, the software security stack, what we have, this software security stack is at the level of where up to the laptop or up to the edge. Below this, we need to have a secure boot. In few laptops we have where exactly that are used by RBI or some military applications. They have a secure boot actually. For example, we set a CMOS password. It is basically it's a CMOS password is a secure boot option which is there from last 30 years, which we generally use. When it comes to the setting up a CMOS password is a booting solution, a boot level actually this one what we say. If you remove the battery in the motherboard, that password get lapsed. That is a vulnerability of the technique, which we know, which we discussed many times in our lab. So in this way, these are actually the hardware level. We had a very limited options like CMOS password and removing a battery was possible. This is all actually still today we have a same thing that there is no much change here. But when it comes to the IoT, this same similar software stack cannot be deployed because they have a very constrained devices. Edge nodes doesn't have any much. They cannot run AES or RSA algorithm. We need a lightweight cryptos there like Simon or Present or something like that. And at the same time, this stack needs to be modified, and we have to develop a TEs to make it an hardware security. The same software stack needs to be reflected in a much better way for the IoT security because world is moving from IoT security. Even the people, Intel or any computer maker today call the laptop as a hedge. They started talking laptop as a hedge. So the hardware security comes from a root of trust is hardware, puffs, above that one TE layer. So TE will be there. TE includes puff. TE includes both hardware, firmware, co-design, hardware Trojan defense, security and authentication, passwords, secure boot, everything hardware level. What we can do, we will do. On the above layer, we'll have again antivirus, again firewall, AES encryption, lightweight. The stack hardware stack is initially the software stack is all software. Now now earlier security stack is all software. Now security stack is 40% hardware should come both in laptop server and also in the embedded and IoT domain. So this is what exactly as of now hardware security stacks are not standard. In software security stacks are standard. In hardware security standards has to be established. In maybe next 10 years it will get established. I hope I answered your question. Sir?
Yeah. Okay.
Yeah. Yes.
So, like POF is the only option in hardware security, or we may have any other option?
TRNG we can use. TRNG we can use. True random number generator is a now because the puffs are becoming bulky and reliability is a problem. They use the TRNG and they produce a unique number. They will store it in a OTP, one-time programmable memory. From there, they will extract that unique number from each device in each microcontroller. Based on that number, they will build the authentication, etc. And all. The PUF, after PUF, the TRNG is a suitable
okay. That
alternative.
also TRNG is, I think, used in block.
Exactly, blockchain also it is used.
Yeah, TRNG is blockchain, right? Okay.
Yes, blockchain is also used.
Okay, one of the participants, Rajendra Singh Yadav, you can ask Rajendra ji, your mic is on, I think. If you can ask directly, you ask, or else I will try for you. He is asking like what type of project can be implemented using OpenTitan?
Yeah, the OpenTitan is a very complicated stuff. As of now, it is tough to understand, and still I'm in a process of still understanding it. Basically, it has got an IBEX RISC-V processor as its core. Based on that, Google has given some access mechanisms, firmware they have given, and what type of projects is a TPC means we can construct the ARM trust zone. We can study the ARM trust zone, which is a TEE. Based on that, we can try to emulate what are the features of ARM trust zone in the OpenTitan. So basically, it's a comprehensively it is against node replacement attacks, sleep deprivation attacks, false injection attacks, and all can be verified on the OpenTitan project. We can verify whether it is tolerable, whether it is okay with this. It also includes a secure boot up to some extent, but it is not yet verified. I didn't find any literature connected with secure boot and OpenTitan.
Okay, is there any other questions by any of our participants?
Hello.
Yeah,
Yes, please.
please tell.
Yeah.
Yeah.
Regarding true random number generation, efficient approach of using Titan software, using this type of use in generation of generating of true random number generation using XOR based post processor 64-bit or 32-bit will be using CPO as well as 8-bit up counter down counter processor.
Basically, the TRNG designs are different types of designs are there. The most common way of TRNG is designing XOR gates, means using the feedback XOR gates in the feedback path of a shift register. And again, that's one way of standard way, but there are multiple ways of designing it. For example, there are these RNGs, means what we can quantum TRNGs are coming in. Use the quantum gates and build the TRNGs. And again, there are different type of TRNGs. TRNG configurations are there. Just one second. Just a minute. See, this is the different TRNG configurations. I will just take it out. So the common TRNG architecture, which is widely discussed in literature, are the noise-based TRNGs.
Yes, same area of interest. Yeah, I have same kind of area of interest.
Noise-based TRNGs and oscillator-based TRNGs.
Yeah,
and memory-based TRNGs.
A calculation of jitter and metastability.
Exactly, but see, the thing is, the major difference is, if you want to design a better TRNG, the only fundamental formula you have to use is, as the puff catches why the puff, what is the basic configuration of a puff? The Prof is meant to capture the maximum process variation, right? The process, if this the process variation is high, your Prof is better. Then if when your TRNG is better, when it captures, when a circuit captures the maximum device noise, maximum power supply noise, maximum a small variation in environment, a 0.2 degree temperature change should affect your TRNG. Means a small change, a small glitch in power supply should affect your TRNG. Should small noise in the device, a device intrinsic noise, a small ADC changes the configuration from 10-bit mode to the 12-bit mode. That should affect your TRNG. Means puff quality depends upon the process variation during manufacturing. The quality of a TRNG is guided by device noise, power supply noise, and environmental factors. If you design a chip, if you design a circuit which captures, which is very sensitive to the device intrinsic noise and power supply noise, will be the good circuit. Yeah.
Hello, sir. Calculation of different parameters like power throughput and power consumption as well as path delay in terms of latency.
Path delays are predictable. Means the path delays, maybe after using for a 1 month, adversary can easily predict your path delays.
Yes,
Path delay
network
based
latency.
TRNGs are highly vulnerable. Highly vulnerable. Yeah.
The network latency.
The quality of TRNGs are generally measured using the NIST standards. There is a National Institute of Standards and Technology. The NIST defines the quality. The NIST defines the properties and parameters to define the quality of TRNGs. All that, whatever the TRNGs we design, we have to calculate the NIST parameters for TRNGs. Just a second. This is a statistical suit from the NIST. We have something like this. So we have the NIST have a publication. They have a standards, but I don't remember what the parameters are there. For example, what parameters they are predicted. As of now, I don't remember. I've gone through the papers of the NIST, especially this particular paper, a statistical test suite for random and pseudo random number generators. We have to, just like for the PUF, we calculate uniqueness, reliability, and reproducibility. The same way for NIST standards and NIST parameters needs to be assessed to assess the quality of a TRNGs. And also we have to design a circuit which captures those things for the better TRNG. And also we have to use this NIST standards to analyze the quality of the TRNGs. Just a second, I think it will get open. So I think you can look at this document. I think you might have seen this. A statistical test suite for random number and pseudo number generations for applications. So there's some tests here listed, like runs test, frequency test, and that is also called as a monobit test, and binary matrix test, DFT test, non-overlapping test, etc. These tests we can apply on the TRNG data, and we can calculate the quality of TRNG. Sir, I hope I answered your question.
Yeah.
Yeah.
So yeah, I think Sudeendra is actually a very good speaker. At the same time, he's also thinks a lot. Like analyze a problem and use it, and direction of problem like this. He has that ability, and also to write and present somewhere as part of your publication and all. So I hope our participant has gained something from him. He's actually one of our backbone of our VLSI lab. And actually, he and me both actually part of VLSI lab under the guidance of KK Abhadra sir and other 2-3 fellows like are there also. So anyway, I thank him. Today he has given time, and I think our participant has gained something in terms of few concepts that they can use for their research
sorry for
sessions.
interrupting. Hello.
Ah.
Sir, kindly give me a contact of and share this today's site. I have all the material of PPT because
Sure. I will share with Professor IS sir. Then IS sir may pass it on to all the
and
participants.
send me email. Send me email of for in future requirement of any problem statement as well as for research scope. So I will personally guide you with me.
Please, sir. Please, I'm happy to discuss with you. I will share my email ID. Yeah.
Yeah. Okay. Actually, I also will wind up in 3 minutes. So I also told I also test that it's something like we should learn many things from this course, but again we have to do our own literature survey and research to come up with a problem statement, and then we can have obviously guidance from all of our experts depending upon their time, which will help us to just build our you can say like more knowledge. Okay, so that is one. And Sudeendra, please can you switch on your your camera? We used to have a last photo session, like photo session in the sense screenshot for maybe we need to upload to hotel site of a report. I have allowed camera for all the participants. I request please switch on it. No, my camera is off. Okay. Also, whoever is sharing slide with us, that will share with you with all the recording session. If somebody is not sharing the slide, you may get his slide from the recording sessions. Yeah, I don't know. Many cameras are on, but I can't able to see photos of many. Rajesh, can you take some screenshot? I'm taking, but many are blank. Rajesh, are you there?
Yes, sir.
Yeah, can you take some screenshot? In my end, many are looking blank only.
Actually, I had opened in a mobile, sir. There is showing 4 and 5 people.
Okay, I don't know. One will gone. Okay, with this, I couldn't get much screenshot today. With this, I thank Professor Sudeendra Kumar for his time and his ideas, which may help us thinking in our way to carry out a novel research in our labs. Thank you.
Whatever I have learned, I am learned with you.
And thank you all the participants. Okay, we have a MCQ session tomorrow. So we'll have like 20 to 30 questions. All will be multiple choice type. So I advise please don't miss the session because we need to fill and upload all the data at the AICT portal. Okay. So it will be all multiple choice type 1, 2, 3, 4. So you can choose one out of that. So it will be related to all these sessions only or basics only.
Excuse me, sir. I thank you for giving the opportunity to share my thoughts. Thank you very much, sir. Thank you, KKM sir, Aiskan sir, and all the organizers of this FDP. Thank you very much, sir.
Okay, thank you. Tomorrow we have a session from Professor Urbi Chatterjee, IIT Kanpur. It is on hardware security again. I think he may tell about pop under. I advise and request, please don't miss the session.
Thank you, sir. I will also join.
Yeah, followed that we'll have a MCQ of 30 multiple choice each. Okay, thank you all.
Thank you, sir. Thank you very much.
Thank you all. Good night.
Thank you. Good night.
Thank you, sir.